Welcome to Algebra 2. Today we've got section 11.2, Populations, Samples, and Hypotheses. Now, we said in 11.1 when we opened up the chapter that this is going to be math that is coming from a new angle. So I think I referred to it as a different branch of mathematics, this statistics chapter that we're dealing with right here. And with that comes a lot of vocabulary. We're going to be analyzing a lot of claims and statements and surveys, and we need to kind of lay the groundwork with some solid vocabulary, and 11.2 is one that we do that. Let's have a look. All right, so first, a population is a collection of all data, responses, measurements, or counts that you want information about. A sample is a subset of the population. Okay, so when people are taking a survey, they're taking a sampling of the entire population and then kind of broadcasting that. So we want to distinguish between those two. If we have a numerical description of a population, that's referred to as a parameter. And if we have a numerical description of a sample of that subset, it's called a statistic. Okay, and you can see there's a little explanation that says sometimes populations are too large to measure a statistic for. You'll take a sample and then try and estimate what the parameter is. Important to distinguish between a parameter and a statistic. It's nice that they start with the same letter, parameter, population, statistic, sample. In statistics, a hypothesis is a claim about a characteristic of a population. So that is taking, let me think here, maybe taking the results of a survey, taking a statistic that relates to a sample, and then making a claim based on that as to how it affects the entire population. Okay, so our first example, determine whether or not we have data collected from a population or from a sample, and explain. The key word here is going to be subset. So for number 6, the color of every third car that passes your house. If you're collecting that data, you are collecting a sample, because you are collecting data that is a subset of the colors of all cars that pass your house. Okay, just want to apologize if you hear that little rumbling in the background. They're actually cleaning the floors outside my room, so hopefully you can still hear me okay. Number 8, the age of each dentist in the United States. So if you find this data, you collect it all, is that a sample or a population? Well, that is the population, because it's not a subset, it is all ages of U.S. dentists. Okay, we have used the entire population, not a subset. Okay, example 2, identify the population and the sample, and then describe the sample. So again, being able to look at a statement, and don't these just look like headlines or articles that you'd see maybe pop up online or things like that. We want to be able to analyze that. What's this saying, really? And that's what this chapter is all about. So these are really, really good problems. Identify the population of the sample, describe the sample. Number 10, in the U.S., a survey of 1,777 adults that are ages 18 and over found that 1,279 of them do some kind of spring cleaning every year. Okay, so what's the population? Population is all adults in the U.S. That are 18 or over. Okay, our sample is 1,777 adults in the U.S. that are 18 and over. So you can see our sampling is a subset, because there are clearly more than 1,777 adults in the U.S. Okay, now describe that sample. Of our sample, 1,279 of whom do spring cleaning. And the remaining, how many is that? The remaining 498 do not. And I think this should actually say of which. I'm not an English major at all, or an English teacher for that matter, but we're describing our sample. It's 1777, and then we go further to elaborate, what about that 1777? Number 12, in the U.S., a survey of 2,000 households with at least one child found that 1,280 of them eat dinner together every night. What is our population? Because naturally our survey is giving us a statistic, it's not giving us a parameter. The population here is all U.S. households with children. The sample is 2,000 U.S. households with children. Okay, and then to describe the sample, of those 2,000 households we surveyed, 1,280 of which eat dinner together, and the remaining 720 do not. Okay, so breaking apart a claim to realize what is the population that this claim is about, and then using the sample to kind of break apart that information. You can see that we're elaborating much more than what the claim told us initially. Example 3, determine whether the numerical value is a parameter or a statistic, and explain your reasoning. So number 14, in a recent year, 53% of the senators in the U.S. Senate were Democrats. All right. So 53% of the senators, okay, that's 53% of all senators. This is a parameter. The percentage of all senators was found. And then for number 16, a survey of U.S. adults found that 10% believe a cleaning product they use is not safe for the environment. This is a statistic. Because the percentage of a subset was found. In this case, the percentage is based off of a survey, not based off of the entire population. Okay, so those two claims, if you read the sentences, they look very similar. 53% of the senators, 10% of adults. They sound very similar, but look at what they're representing. Number 14 is representing all senators. Number 16 was just representing the subset of people that were surveyed. And our last example, it's kind of a nice section, right? It's purely vocabulary. There's not really a whole lot of math to be done here. A lot of writing, though, which is a first. You flip a coin 4 times and do not get a tails. You suspect that this coin favors heads. So what do? Call up the manufacturer. The coin maker claims that the coin does not favor heads or tails. So you simulate flipping an equal coin 50 times by repeatedly drawing 200 random samples of size 50. Maybe you use like a computer software or a spreadsheet or something to calculate this data. In other words, what would happen with a truly random coin with 50-50 likelihood? The histogram shows the results. What should you conclude when you flip the actual coin 50 times and you get 17 heads or you get 23 heads? Okay, so let's take a look. Here they've got a nice little histogram that shows the relative frequency of getting the proportion that result in heads. So you can see in our simulation, we're most likely to get a 0.5 probability. In other words, half of our flips end up heads. We're most likely to get something here in that middle region. It's kind of resembling that bell curve that we saw in the last section, right? So it definitely looks like we should expect a normal distribution here. So we conduct our own trial after doing all of this simulation work. We take that coin that is suspect, flip it 50 times, and then we get 17 heads. Well, 17 out of 50 is like a 34%. That's right here. So you can see, based on our simulation, if that really is an equal coin, it's not very likely that we're going to get 17 heads when we flip ours 50 times. So what can we conclude when we conduct our own experiment and get 17 heads with that coin? Well, the manufacturer's claim it's most likely false. He's claiming it's a true coin. We run all these simulations to see what should happen. Then we try it with our coin, and we find out that we get this very unlikely situation to show up. It's more than likely that manufacturer is not telling the truth. That's not to say it's impossible, but more than likely our coin, it does favor heads, or it does favor tails in that case. Letter B, what if we get 23 heads? Well, that is 23 out of 50, so the proportion of our 50 coin flips, it would be, 46% then if we got 23 out of 50. So that's right here. That's in the meat of our bell curve, and that kind of, based on our relative frequency, is much more likely. So if we conduct our trial and get 23 heads out of 50, then the manufacturer's claim is most likely true. All right, so flipping a coin 4 times and not getting a tails, that's not necessarily that bizarre of an outcome, but when we extrapolate that and do a full-scale simulation and do 50 coin flips, then we can make a better claim as to whether or not that coin does favor tails or not. Very cool, kind of tie it all together problem, but again, it's just reading a graph is all that we're doing mathematically here. Believe it or not, that's all we have for section 11.2. Here's a look at your homework assignment. Not a whole lot of problems, but there is a lot of writing. Be sure that you are paying attention to the language that's being used, this new vocabulary that we're kind of developing to work with statistics. I know I say this quite a bit, but some effort now is really going to make our future work a lot easier.